Hello and welcome back to CMOS RF integrated circuits. Today is the 40th lecture and we have finished all the requirements of this course, and in this lecture I am basically going to give you a broad course summary and conclude the course. Basically that is my plan. So, these are all the different items that we have covered. We started off this course with matching networks, then we discussed what are all the components that are available to us on an integrated circuit. So, we have resistors, capacitors, inductors, mutual inductances a lot of times, transmission lines. So, these are all the different components that are available to us. We discussed at length about all of these components. We discussed transmission lines at length, why we need impedance matching. I will come to the details. I will just broadly mention what are the different chapters or modules we covered. Then we talked about the MOSFET. MOSFET is the core of CMOS. So, it is in the title, you can't get away without the MOSFET. Then we worked on bandwidth estimation techniques, method of open circuit time constants, short circuit time constants. Actually, we just worked on open circuit time constants. Then we worked on techniques to make wideband circuits. After that, we worked on noise. Then we worked on designing a low noise amplifier. Then we worked on mixers. Along with mixers, we also discussed some architectures, modern radio architectures, heterodyne, super heterodyne, homodyne and so on. Then the next phase we discussed oscillators, then frequency synthesis. As part of frequency synthesis, we also worked on phase lock loops, and then finally we discussed power amplifiers. Okay. So, let us take one by one. Let us go back. I want to take a holistic view of this. First of all, the radio architecture. Let us go back and see if we have covered all the different components. So, there is the antenna. It is a transmit and a receive antenna at the same time. I promised that I will not cover the antenna. I did not. It is a course by itself. Working on the antenna is a course by itself. We did not do anything. Then there is some sort of a splitter or a circulator or whatever you want to call it. So, this is the general architecture. Okay. We have a splitter at RF frequencies. It splits the transmit path from the receive path. Now, if you are working on something like CDMA, code division multiple access, where both the transmitter and the receiver are on all the time, then the splitter is something which is extremely important, because transmit and the receive path are active at the same time. If you are working on time division multiple access systems, like for example, GSM, or for example, WiMAX. WiMAX is a mix up of a lot of different things. So, for example, in WiMAX and in GSM, the splitter is not really that important, because the transmit chain and the receive chain are not on at the same time. When the transmit is on, the receive is definitely off. When the receive is on, the transmit is definitely off. So, the architecture of the communication protocol itself determines whether the splitter is something which is very relevant or not. In any case, the splitter was not discussed in this course at all. Okay. Now, as far as the receive chain is concerned, the first most important block is the low noise amplifier. Why is it the most important block? Because the noise figure of the low noise amplifier determines the sensitivity of the entire receive chain, more or less. If the low noise amplifier gain is significant, then the noise figure of the low noise amplifier is all that matters, right. So, if you build a good low noise amplifier, that is all you want, that is all that matters as far as the receive chain is concerned, a good low noise amplifier. Okay. There are other things that matter, we will come to them. Okay. So, the low noise amplifier is something of great importance as far as sensitivity is concerned. That is one of the most important blocks in the receive chain. The next block I have shown in red, I have shown IRF, standing for image reject filter. So, this image reject filter, we did not really go into filter design and so on and so forth, but the image reject filter could possibly be made up of a passive network, capacitors, inductors, resistors and so on. You can contemplate making the IR filter using passive components. It precedes the mixer in case your system is heterodyne or super heterodyne. If you are making a homodyne system, direct down conversion, then the image reject filter is of no relevance. You do not need, there is no image, the image is the signal. So, you do not need to reject anything. All right. So, this image reject filter is something very important if we are talking about heterodyne systems. Frequently we do broadband communication protocols like WiMAX, WCDMA, where the data rate is large, right. Typically these are wideband, because the data rate is large, you need large bandwidth, and when you need large bandwidth, the DC offset problem is not a problem anymore, because the DC is a very small part of this broadband signal. Now, when that happens, we prefer designing a direct down conversion receiver, because direct down conversion is otherwise easy to build. The only stumbling block for direct down conversion is the DC offset. The DC offset is not critical if the data rate is large. When the data rate is large, typically you have a wider band, right. You need, go back to Shannon, you need so much bandwidth to support such a data rate, right, that is dictated by Shannon. Anyway, so when the data rate is large, you need larger bandwidth. If you have a larger bandwidth, then the DC, really DC is a very small portion, a very narrow portion qualitatively of a larger bandwidth. As a result, the DC offset problem is no longer very significant. even if there is a DC offset, even if you do make a mistake as far as DC is concerned, DC and frequencies around DC are concerned, it is not going to affect you much. It is going to degrade your SNR a little bit, that is not going to decrease your, or that is not going to increase your bit error rate significantly, right. So, that is basically the idea. So, when you have these high data rate communication protocols like WiMAX and WCDMA, we prefer building direct down conversion receivers. When you have older protocols which are very narrow bandwidth, low data rate, for example, GSM, it is a low data rate. What is the data rate? If you use GPRS or Edge, you will probably GPRS I think is about 30 kilobits per second at most, it is not going to be much more than that. So, that is very low data rate. The bandwidth of a GSM signal is something like 100 kilohertz, right. So, with that kind of bandwidth, DC is a significant portion of that. It is hard to reject DC and not reject the signal itself. How do you reject DC? We put a DC blocking capacitor, right. Now, the thought is this, that when you put a DC blocking capacitor, that by itself is not enough, you actually have to put a high pass filter to block out DC. So, it is a CR network. Now, you put a capacitor, you put a resistor. To lower the cutoff frequency of this, so this is a high pass filter. This high pass filter will do a good job in blocking out DC, but you want the cutoff frequency of this to be significantly lower than your signal bandwidth, right. You do not want it to cut off things other than frequencies other than DC as well, agreed. Now, let us say that your signal bandwidth is 100 kilohertz. Okay. Now, 100 kilohertz means you most probably want signals up to 1 kilohertz, 1% of 100 kilohertz. Should pass. Now, if you want signals up to 1 kilohertz to pass, let's make it a little easier. Let's say instead of 10 kilohertz, I say 1 kilohertz, I say 10 kilo radians per second. Okay, that's going to make my mathematics a little tad easier. Okay, so that means that this RC product has to be equal to or greater than equal to 1 by 10 k, okay, which is 0.1 millisecond. So, RC time constant has to be more than 0.1 millisecond for this to work successfully, for this to not block out signals beyond 10 kiloradians per second. 10 kiloradians per second is something like 1.5 kilohertz. Okay. So, RC time constant has to be more than 0.1 millisecond. Now, typical values of the capacitor are what? What is a capacitor that you can build easily on a chip, on an IC? On an IC, the density of capacitance that you can build, for example, if you use the gate oxide of a MOSFET, okay, you have got the gate, and if you connect the source and drain together, remember we talked about this capacitance action also. This is the way we studied the MOSFET in fact, right. So, you have got a thin oxide layer in between, and that separates the gate and the channel, and that is your capacitance Cox. I mean the density Cox density times the width times the length. So, typical Cox densities could be something like 8 femtofarad per square micron. Okay, which means that if you want to build 8 femtofarads, 8 into 10 to the power minus 15 farads, then you need 1 square micron. All right. Resistors, you can use some high resistivity polysilicon etc., special special masks and so on. You can get resistances of up to 1 kilo ohm per square. Okay. Normally, this is a very large number that I have put over there. 1 kilo ohm per square is quite high. Okay. Typical polysilicon resistivities are much lower, they will be around 30 ohms per square and so on. 1 kilo ohm per square is with special implants, right. Now, let us say you make a resistance of 1 kilo ohm and you make a capacitance of 10 picofarads. Okay, 8 let us say 80 picofarads. 80 picofarads means I need 10,000 square microns, means I am going to use 0.1 millimeter by 0.1 millimeter. That is a large amount of area, 0.1 millimeter by 0.1 millimeter. That is a very large amount of area that you have used up in building an 80 picofarad capacitor, okay, 80,000 femtofarads. So, 10,000 square microns, so 100 microns by 100 microns. So, that is 0.1 millimeter by 0.1 millimeter, that is a fairly large sized capacitor, right. If you want to make 8 nanofarads, that is 1 mm by 1 mm, that is almost the size of your whole chip, right. If you are making a 1 mm by 1 mm chip, that is all that you have, you are going to get 8 nanofarads. Okay. Remember, the product of the resistor and the capacitor has got to be more than 0.1 millisecond, right. So, this is basically the stumbling block that I have got, area. Area is the very basic stumbling block when it comes to making a direct down conversion receiver. You have got to block out DC. The way to block out DC is by using a high pass filter like this, and a high pass filter like this looks easy on paper, but when it comes to making the components, it is impossible to fit the components inside an integrated circuit. So, even when you make 8 nanofarads, even then you have got to realize that you have to make about a mega ohm worth resistance, right. So, that is a large resistor that you still have to make, even that is going to cost you a large amount of area. So, basically the thought is, do not make direct down conversion receivers when the bandwidth is less. When the bandwidth is more, when the bandwidth is 2 megahertz, 20 times this, the requirement as far as the high pass filter cutoff goes down, and then you go for a direct down conversion receiver. Okay. So, all this we talked about to explain why I need this image reject filter in the receive path. Then there is the mixer. We talked about the mixer. right. Of course, you have in phase and quadrature phase signals. So, you have to make a quad mixer or rather a quadrature mixer, right, and a quadrature mixer there are several architectures that you can pick up. This is the Weaver architecture, for example. You can use the Weaver architecture and build a quadrature mixer. Now, for the mixer to work, you need to have, for a quadrature mixer to work, you need to have two oscillators, one giving the sine, the other giving the cosine component. Agreed? So, you have to make a quadrature frequency synthesizer as well. Did we discuss quadrature oscillators? Finally, I told you that do not let me get away without telling you how to make it. Well, it is easy. One very popular way of generating I and Q components is to really design an oscillator for double the desired frequency and then use flip flops to generate the two phases or four phases that you need. You need four phases 0, 90, 180 and 270 degrees, right. These four phases can be easily generated by a modulo 4 counter, I am sorry modulo 2 counter, right, divide by 2 counter. You can easily make one of these and you can generate the 4 different phases that you need, right. So, the thought is instead of generating f naught using the why do not we generate twice f naught using our oscillator or frequency synthesizer. So, then we got into this whole business of frequency synthesis, and to study frequency synthesis we first talked about PLLs, phase locked loops, in quite a bit of detail. So, the way we approached phase locked loops, you will not find it in the books normally. This is not the way the books talk about phase locked loops. They talk about it in a very different approach. They do not give you the control theory approach, unfortunately. Okay. So, we build a phase locked loop, it is a velocity control system. So, you need two integrators. One integrator is given by the oscillator itself, the second integrator should be there as part of your loop filter or as part of your controller. Now, unfortunately, when you have two integrators, just two integrators by itself, the system is never going to be stable. So, to put in stability, you have to put in a 0 and a pole, right, one after the other. So, you have got two poles at DC and then a 0 and then another pole. That is finally what is going to be stable, that is what we built. So, the loop filter is made out using a charge pump. So, it is kind of integrated with the phase detector. The phase detector is really a digital block, it contains two flip flops, and this is how we build a phase locked loop. Now, frequency synthesis is just an extension of the phase locked loop. You put a phase divider in feedback, right. Now, how you do a phase divider is fairly straightforward. If you want to divide by an integer, all you make is a divide by n counter, modulo n counter, and that is going to work fine to do a division by n. Now, there are special ways to make this divider. So, I would encourage you to look at the books. The basic problem over here is that the logic circuits have to work very, very fast. So, you can't really make your static CMOS logic circuits and get away with it. you are doing a division at RF frequencies, right. So, your logic circuits really have to work hard. So, there are very efficient ways of doing this division, and for that I recommend that you take a look at the literature. We did not really discuss these techniques in the class. So, I will be giving the pointers. There are the pointers in the notes for that corresponding lecture. Okay. Then we discussed fractional synthesis. So, the problem with integer division was that the loop bandwidth is very small. There are also these spurious frequencies that are being generated, and the spurious frequencies thankfully are outside the loop bandwidth, which means that they get filtered, right. So, the basic problem with the integer n synthesis technique is that the loop bandwidth is small. Loop bandwidth is small means that the VCO, the oscillator that you have built, has to work harder in terms of its phase noise requirements. Okay. It can track the reference oscillator weakly, only within the bandwidth it tracks the reference oscillator. So, outside the loop bandwidth it has to have very good phase noise characteristics of its own. So, this is one big problem. The second big problem is the settling time. If your base station asks you to jump from frequency A to frequency B, now unfortunately you are too slow, because your loop bandwidth is very small. So, this pushed us to make these fractional dividers. The way we did fractional dividers was the first technique was some sort of pulse width modulation. Let us divide by n sometimes, let us divide by n plus 1 sometimes, right, and on the average we are dividing by a number in between n and n plus 1. Then we discovered that this method is even worse than the integer n synthesis as far as the spurs are concerned, because now I have got a larger loop bandwidth, I can settle faster, but the spurious frequencies are appearing at exactly the same frequencies as before, and they are going right through the loop. So, this became an unfortunate problem. So, then this encouraged us to randomize the division by n and division by n plus 1, and the way we did it was by asking a sigma delta modulator to tell us when to divide by n and when to divide by n plus 1. So, that was the story as far as frequency synthesis goes. Then, so these frequency synthesis techniques apply to both the transmit and the receive path. Typically what happens is that you make one frequency synthesizer and somehow generate both the transmit and the receive frequencies employing the same frequency synthesizer, the same feedback loop. Okay. So, this is typically what the idea is, that you do some kind of modulation and mixing in between, so that you can generate both the transmit and the receive frequencies in one shot. You will have, of course, you will have two oscillators necessarily, or you could have one oscillator and do two divisions. So, that is also a possibility. It is usually the case that you need two oscillators. Now, when you have two oscillators on the same chip, there is this problem of pulling, it is called pulling. The oscillators tend to pull each other towards themselves. Okay. So, if you want to generate F1 and F2 on the same chip, if F1 and F2 are close to each other, then invariably what is going to happen is F1 and F2, the two oscillators will zero in and they will generate the same frequency. So, this phenomenon is called VCO pulling. Okay. Other terms for this phenomenon are injection locking. It is a very broad term. I mean, it is the same phenomenon that is happening. It is not, this is not really injection locking. They might not end up locking to each other, they might just pull each other towards each other, right. They might not lock with each other. When they do lock, it is just a next step. When they do lock, it is called injection locking. So, injection locking is again something which you see in a lot of systems. If you, for example, put two grandfather clocks on the same wall, then after some time you are going to see that they are oscillating together in phase with each other. So, this is generally called injection locking. Injection locking is also a technique which can be used to generate quadrature phases. So, once again I will point you to references for that. We do not have the bandwidth to discuss all of this in this course. Right. So, that is also one reason why you would be encouraged to generate both the transmit frequency and the receive frequency, the transmit and the receive LOs in one shot using the same synthesizer, so that the frequencies are ratios of each other. Again, I will point you to a reference for this. Okay. And then finally, we did the splitter, I am sorry, finally we did the power amplifier. Now, as far as the power amplifier is concerned, we discussed class A, B, C, D, class A, B amplifiers, right, and your pulse width modulation type amplifiers. Now, of these, class A is very linear, but its efficiency is very bad. Class B is quite non-linear, so non-linear that you can't really use it in a modern RF system. So, typically what we do is we use something like a class AB amplifier, and then we put a feedback loop around it to make sure that the linearity is not compromised. Another way to improve linearity is to do back off. So, you design a power amplifier to broadcast 1 watt power, but then you do not really use it at the rated power, you use it 20 dB below that. So, instead of broadcasting 1 watt of power, you broadcast 10 milliwatts of power. Now, 10 milliwatts of power, when you are, let us say, so it is like this, that the second and third harmonics and the intermodulations. So, I am going to plot the input on the x axis and the output on the y axis. Both are in decibels with respect to volts, or you want powers. Okay. Let us put a dBm in the output, decibels with respect to 1 milliwatt. So, let us say this is the slope as far as this is the curve as far as the fundamental component of the power amplifier is concerned. This is the curve. So, looks fairly linear to you. Unfortunately, if you look at the second harmonic is always going to have a higher slope. and the third harmonic is always going to have an even higher slope. Now, the slope for the fundamental is going to be 1 dB per dB. So, if I increase the input by 1 decibel, the output is going to increase by 1 decibel. That is your straightforward polynomial, right. Let us say this is the polynomial that your power amplifier is, y equal to ax plus bx squared plus cx cube, something very general. You can do some curve fitting and fit your power amplifier to this particular polynomial. In that case, if x increases by 1 decibel, y will also increase by 1 decibel as far as the fundamental component is concerned. X squared is not going to give you the fundamental, it is going to give you the third harmonic, I am sorry, the second harmonic, right. Cosine squared is basically cos 2 theta, cosine squared theta is cos 2 theta and dc and 1. So, x squared, if x increases by 1 decibel, then x squared is going to increase by 2 decibels, and therefore, the second harmonic is going to increase by 2 decibels. And then if you look at x cubed, cosine cubed, x is a cosine, cosine cubed is basically cosine cube theta is something times cos 3 theta plus something else times cos theta. Okay. So, cos 3 theta is going to increase by a lot. So, if I increase the amplitude of x by 1 dB, 1 decibel, then the amplitude of cos 3 theta is going to increase by 3 decibels. So, what you are going to find is that the third harmonic goes up by 3 decibels, all right. So, therefore, if I design my power amplifier to work for an output power of 0 dBm, let us say, or let us say I design my power amplifier to work for an output power of 1 watt, but then at 1 watt output power I get so much of second harmonic and so much of third harmonic. I do not really want to get so much second and third harmonics. So, I back off from my rated power by 20 dB, let us say 20 dB. So, if I back off from my rated power by 20 dB, then my second harmonic has gone down by 40 dB. And my third harmonic has gone down by 60 decibels. So, this is typically what I mean by back off. You design your power amplifier for a certain power and then you back off from there and reduce the distortion. So, this is very straightforward, it is used all the time, and on top of it you use feedback, and as a result you are going to get a very linear nice power amplifier. All right. Okay. The third harmonic and second harmonic are not really that important to us, we are going to filter them out anyway. What is more important are the intermodulation products. What you will realize if you do the mathematics is that the third order intermodulation product 2f1 minus f2, 2f2 minus f1, these third order intermodulation products also follow the same curve as 3 dB per dB. Okay. Second order intermodulation, which is not that important, f1 minus f2, f2 minus f1, right, it is the same thing. Second order intermodulation is going to follow the red curve 2 dB per dB. Third order intermodulation is going to follow the pink curve 3 dB per dB. So, that is really something that is of concern, the third order intermodulation product. Okay. Now, we go back and this is basically the course, all the lectures that we went through. We studied power amplifiers, frequency synthesis, oscillators, mixers. We did some low noise amplifiers, right. So, this is as far as the building blocks of the RF system are concerned, but before that, to work on all of these, we studied some of these tools. The first tool that we studied was matching networks. Q of a network was something which we discussed at length. How to convert a series LR network to a shunt LR network, how to convert a series RC network to a shunt RC network, and so on and so forth. Then we discussed the transmission line. Actually, we had discussed the transmission line somewhat before the matching networks, because I needed to motivate the matching networks, why we needed matching. So, then we did the transmission lines. We did we discussed each and every component that is available on a chip individually, right, the resistors, inductors, capacitors. We also talked about mutual inductances. Resistors are easy to build, not always of use in LNAs. We typically avoid using resistors in low noise amplifiers. Inductors are frequently used in low noise amplifiers. Capacitors, of course, are used everywhere, and mutual inductors also come in handy at times. Then we talked about the MOSFET. We went into the detailed small signal model of the MOSFET, how each and every element in the small signal model is relevant as far as we are concerned. Then we studied bandwidth estimation techniques using the method of open and short circuit time constants. We did wideband circuits where we traded off delay to get more bandwidth. So, typically the trade off is let us trade off gain and get more bandwidth, but you do not always want to trade off gain to get more bandwidth. You can also trade off delay and get more bandwidth. So, that is what we talked about. Then we also studied noise. Now, once we did all of this, then we went into the real circuits like low noise amplifiers, mixers, oscillators. All right. So, please post feedback for the course and ask questions on the forums, and it is also important that you read the references that are listed out for each of these chapters, because a lot of material has not been covered A lot has been unsaid in this particular course. So, by no means is this course complete. What I am trying to suggest is, please take a look at the different references that have been made available and follow the techniques, follow the discussions there, because at the end of the day, if you want to build a modern wireless system, it is going to take a lot of effort. It is not something which is very easy and which will pop out of a textbook. Okay. Thank you for your attention.